Okay, so we're taking the derivative first because we need to find critical numbers. Those critical numbers assist in helping us set up our chart, figure out where the function is going to increase, going to decrease, where there's going to be any relative maxes or mins. So taking this derivative, we've got a product because it's x times that root. So we'll start with the derivative of x, which is 1, times that root, x minus x squared, which I'll change over to a power 1/2. Continuing the product rule, we add on x times the derivative of that x minus x squared raised to the 1/2. So we bring down the 1/2, multiply by x minus x squared, subtract 1 from the power, multiply by the derivative of the inside. So inside derivative is going to be 1 minus 2x. All right, so we work to simplify this now. Locate your negative exponent, which is right here. Take note of what is attached to that expression through multiplication. That would be all of this stuff. We want to form a gigantic fraction out of that stuff. So in forming that fraction, we know we've got a denominator of 2. We've got this expression of x minus x squared, which we can now raise to the 1/2 because we're bumping that to the basement. Anything else is going to stay on top. So anything else would be this x, and we've got a 1 here. So we've got this quantity of 1 minus 2x we got to attach as well. So this is all being added on to this piece over here, which is just a quantity of x minus x squared raised to the 1/2. So we've taken care of our negative exponent. Now it's time to find a common denominator so we can create one fraction here. Common denominator is going to be this 2 times this quantity raised to the 1/2. So over here, as I set up a fraction for that piece, I need a 2 times a quantity of x minus x squared raised to the 1/2 in the denominator. If I'm going to put that down here, then I also need to multiply it to the top. The next step, I can put this together as one fraction over this common denominator I've created of 2 times that quantity of x minus x squared to the 1/2. Now let's see what's left over here in the numerator. All right, this part right here. We've got a couple expressions with rational exponents, but notice these quantities that are being raised to the 1/2 power, they're the same things. So it's like we have like bases there. This x minus x squared to the 1/2 times x minus x squared to the 1/2. If that's true, then you've got x minus x squared raised to the 1/2 plus 1/2. You got to add those exponents. So that'd just be a power 1. That's nice because that rational exponent goes away. In the meantime, you've got this 2 we can attach here to the front. We are adding on this x times 1 minus 2x because that's the numerator in the second fraction. All right, clean up a little bit more. It looks like we'll be pretty much there with our simplification. Denominator is what it is. Numerator, though, we can distribute some stuff. If I distribute 2 multiplied through, I've got 2x minus 2x squared. And x multiplied through, I've got x minus 2x squared. Combine your like terms. Looks like we've got a negative 4x squared and a couple of x's, right? Got a 2x and an x, that gives me a 3x. So we're finally at the simplified point with our derivative. Now we can use that to find our critical numbers. Okay, so we split up our pieces on our derivative, right, to set up solving for critical numbers. Take the numerator, set it equal to 0 to find where the derivative equals 0. Take the denominator, set it equal to 0 to find where derivative does not exist. Solving the first equation here, the 3x minus 4x squared equals 0. I could factor an x out. Factoring an x out, you've got 3 minus 4x. That's left over. All of that equals 0. Got two factors here that equal 0. So x would have to equal, well, first factor here, x would have to equal 0. For the second one, you've got 3 minus 4x equal to 0. If I add the 4x over, divide by 4, we're going to find that 3/4 is our other value. Okay, for the does not exist side, since I'm solving for x here, I could divide both sides by 2. That cancels out the 2, right? Because it'd just be 0 divided by 2 over here. You could also square both sides to get rid of that root. You'd have x minus x squared equal to 0 then. Similar situation to what I had over here, I could factor an x out. If I factor an x out, I've got 1 minus x left. All of that equals 0. So, two factors equal to 0, set each factor equal to 0 to solve for x. Got this first factor here of x equal to 0, x would be 0. Second factor of 1 minus x, if that equals 0, then x would have to be 1. So, if we're looking at critical numbers, the foundation for those critical numbers would come from these values. Now, we're not asking for critical numbers here, we're just using these numbers to set up our information here for our chart. And as we go to the chart, you'll notice how you do have the 0 here and you have the 0 here. So when it's time to acknowledge the derivative for 0, we're not going to acknowledge that it's both 0 and does not exist, because that's not possible. What we're going to do instead is we're going to take the does not exist side, because that actually trumps the 0 side. Okay, if there's a possibility it's not going to exist, then the derivative just does not exist for 0. Okay, setting up our chart now. Okay, so acknowledging what happened at 0, 3/4, and 1 for the derivative. Well, how did we get 0 in the first place? We got 0 on the 0 side and on the does not exist side. As I said before, the does not exist will trump the 0 side. We got 3/4 from the 0 side when we solved, right, for the derivative. So derivative would have to be 0 here. And the 1 came from solving on the does not exist side. So derivative would not exist at 1. Okay, so we go back to the game like we played last time. We pick numbers on these intervals, and we try to figure out what kind of signs we're working with for our derivative. Because we know if the signs are positive for that interval, then that interval is going to increase for the function. And we know if it's negative for that interval, it's going to decrease for the function. So I take a number that is less than 0, something like -1. I plug into the derivative. So I got to go back now. Go back to where it's simplified over here. Plug in. If I plug in -1, anybody know what kind of value we get back? Got a 50-50 shot here. It's positive or negative. Actually, could not exist also, right? Let me correct myself there. Does it work? It doesn't work, does it? So derivative does not exist. All right, from 0 to 3/4, select a number between 0 and 3/4. 3/4 being 0.75, so I could choose 0.5. If you plug in 0.5 to the derivative, what do you get back? I got something positive. You can check me on that, but I got something positive. From 3/4 to 1, I chose 0.9 to work with here. I found when I plug in the derivative, I got something negative back. And then 1 to infinity, something larger than 1, say I choose 10 here. I think you're going to find some issues again with this derivative. I think you're going to find again that it just doesn't work. So what can we conclude about the function now, and how can we actually answer the questions here that are stated in the directions? Well, we can at least acknowledge here where it's positive that the function must be increasing for this interval 0 to 3/4 if I look at the graph of that function. For the interval 3/4 to 1, again, if I had the graph of the function sitting in front of me, I should see, since this is negative here, that that graph is decreasing. And there is a change in direction as I go from this interval to this interval because it's going up to down. So that means there's some kind of extreme point, right? What kind of extreme point are we working with here? Say local or relative what? The maximum, right? It goes up, hits that point, comes down. That's the highest point in that location. So since there is a relative maximum, it'd be nice to know what the value of the function is that's assigned there. So if I figure out this piece, all I have to do is take the 3/4, plug back into my function to figure out this value. Now, we've got some, I don't know, extensive calculations going on a lot of these problems. So if we start coming up with decimal values, that's fine. Here, if I plug in 3/4 back to the original function, rounding off to 3 decimal places, I find the relative maximum value is 0.325.